So now we're going to combine all these things together, and this is called the ideal gas law. Now this is one of my favorite equations. So this guy right here, PV equals nRT. Some students remember it by calling it PivNert. You just kind of throw some vowels in there. PivNert. PV equals nRT. So we know what P is and V is and N and T. What's the R? Well, all of these things were proportional. There's got to be a proportionality constant. And that constant is called the ideal gas constant. And it's given the symbol R. And this is its value, 0.08. You know what? I think that's wrong. Just a minute, because that's bad to get that wrong. Oops, there goes my cable. No, that's okay. I was thinking the 06. It's sometimes done as 0.08206, but this is just rounded up, so it's fine. 0.0821. The units on that are weird, aren't they? Liter atmospheres per mole Kelvin. But these units tell us what units we have to use in the equation. So to use the ideal gas law with this gas constant, you have to have pressure in atmospheres, volume in liters, amount of gas in moles, and temperature in Kelvin. The other gas laws, we said that the amount of gas had to be moles or millimoles or something like that, and the temperature had to be in kelvins, but the pressure and the volume could be pretty much anything because they would cancel each other out. But here we don't have changing conditions. We're looking at a gas on one set of conditions, and if we're going to use this gas constant, we need to use its units. The gas constant can be expressed in other ways, and sometimes it's used as 8.314 joules per mole Kelvin. Then you have to use those units. But this is the one we're going to use. This is kind of a summary of all these equations. The relationships between all of them. There's another one, another named equation that we didn't really talk about called Gay-Lussac's law, which relates pressure and temperature. But they all combine into the ideal gas law. I'm just debating whether, no, I don't think we don't need to go there. That would just be a waste of time. Are you serious?
Yeah.
Okay. It's just a little math. Because you don't want, it's like the less far we get, the less stuff will be on the exam, right? Yeah.
When it said, on that previous slide, it said the constant R is 0.0821. Is that supposed to be equals L times ATM?
No, those are the units on it.
Yeah, it's like if you solve for R, like you divide by N and T, like mole and K are going to be on the bottom.
Right.
Yeah.
Yeah.
So
So let's look at that. That actually plays into what I was going to do just now. Okay, so if we take the ideal gas law, PV equals nRT, and we solve for R. So we're going to divide by N and T. So now we have PV over NT equals R. R is the constant, the proportionality constant. And it had units, well, it is 0.0821 liter atmospheres per mole. That's a bad M. Mole Kelvin.
Oh, that's just the unit.
It's just the units. So here, I can't see, pressure in atmospheres times volume in liters, divided by N in moles, times temperature and kelvins. So they just left them there instead of saying, oh, let's create a new unit. So it's just liter atmospheres per mole Kelvin. And it's a very, very good idea when you use this constant to write those units in there. So if that is always a constant, then we could also say that under one set of conditions, say P1 V1 over N1 T1, that equals R, and P2 V2 over N2 T2 must also equal R, because it's always constant. Question?
That number, is it 0.081 or 0.082?
Thank you. I think I said 2 and I left the 2 out. Yeah, that's bad. I'll try that again. Thank you for pointing that out. 0.0821. There we go. That's better. So here we have, if we look at this, let's pick a color here, orange. P1V1 equals P2V2. Because if N and T don't change, if N1 is equal to N2 and T1 is equal to T2, then they cancel out, right? And we're left with Boyle's law. Or here we've got V1 over N1, V2 over N2. If the pressure and the temperature are same, there's Avogadro's law. Or it was volume and temperature, right? Volume and temperature. If the pressures and the amount of gas are the same, there's Charles' law. Cool, huh? Okay, so if you don't remember, or if you don't want to remember all these other equations, this is how I derive, let's do a different color, derive this kind of in my head. So I say P1 V1 equals N1 R T1. And if I divide that by itself, there's nothing wrong with doing that, right? Because P2V2 equals N2R T2. So I'm dividing both sides by something that's equal. So the R's cancel out. And then if my temperatures are the same, the temperatures will cancel out. If the pressures are the same, the pressures will cancel out. So you can take PV equals nRT, divide it by itself, and then cancel out anything that doesn't change. The form of the equation may not look exactly the same, but it could be rearranged to be exactly the same. But you can derive any equation that you need for gas laws just from PV equals nRT.
In your head.
Well, in your head or write it down. But it's still taking up way less brain space than trying to remember, well, this was the combined gas law, and this was this, and they're all the ones and the twos and the P's and the V's. They're very easy to mix up.
Mm-hmm.
I personally don't remember them. I think them out every single stupid time. And the names, after teaching this for years and years, I think I'm finally connecting some of the, which one's Boyle's law. Does it really matter? No, it doesn't really matter. I mean, yes, we honor these people, but I don't want you to waste time memorizing, well, this one's Boyle's law and this one's Charles' law. I want you to know the law and be able to use it. So calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So we read through that, and we may or may not recognize, hey, wait a minute, there's only one set of conditions. There's not two sets of conditions. So this isn't going to be one with the ones and the twos. But let's say we don't recognize that. Let's just We're gonna stick with the program, we're gonna make a table, because she said to make a table, so darn it, we're gonna make a table, right? The table really is a good thing. So we'll make a table. So here's our little table. And we've got our 1 and our 2. And the first number we come across is 0.845 moles. 0.845 moles. And what variable is that? PV, nRT. Which one? It's N. And then the pressure is 1.37 atmospheres. Oh, that was nice. They told us that was the pressure. And a temperature. Well, that was kind. They gave us the temperature in Kelvin. So that's very thoughtful of them. We ran out of numbers. There's no second row. You see that? So I'm going to erase the second row because we don't need it. But, so was it a waste to make the table? No, we've got our numbers written out and they're all labeled, so it's not a waste of time. So what kind of equation do we need for this? What are they trying to find? Volume. So volume, we'll just call that V for volume. Oh, tell me that I do these things. That's not a K, that's a T, that's the temperature. It's in Kelvin.
I did the same thing.
Well, yeah, because I wrote it on the board.
No, no,
So then we go into a fraction, we make it equal to R.
So, nothing's changing. This is the ideal gas law. PV equals nRT. R is a constant. We know what it is. There's 4 variables. We have 3 of them. We just need to find the 4th one. So let's take the ideal gas law and rearrange it so that V is by itself. So we're going to divide both sides by P. So we're going to end up with V equals nRT over P. So put your units in here. 0.845 moles. I'm going to run out of room. What can I do about that? And we'll do this.
Black out the
Yeah. We'll just, I think we'll actually have enough space just going up there. Okay, so
I needed that today.
V equals nRT over P. So N is 0.845.